Welcome back, everybody. All right, so this is. Oh, hi, sweetheart. How's it going? Ah, really?
He's not in trouble.
Yes, he is.
Someone
Tell me
his
it.
spot again.
Uh, so this is day two of the indefinite integrals net change theorem. We already did indefinite integrals, and today we're going to talk about the net change theorem. Remember, to talk about an indefinite integral, basically what we're just going to be doing there is identifying the antiderivative. That's really what you're looking at there. Identify the antiderivative, and that's just the notation we use without the numbers on the top and the bottom. And remember that you can always identify the antiderivative, and then on top of that, define the endpoints to find the definite integral. So we were here. Okay. The net change theorem. The net change theorem. Okay, so the net change theorem. Think about what the name implies. Net change, total change, right? Total change from one point to the next. And when you talk about total change, that's going to be the integral of the function. Okay? The integral of the rate of change is the net change. The integral of a rate of change is the net change. Think about that. Integral of a rate of change. Rate of change being derivative, so antiderivative. Integral of the rate of change is the net change. Now, there's a lot of things that this can be applied to. And funny enough, I was thinking about this last year. I was going through the notes that I was teaching today, just about half hour ago. And I in here, and I'll kind of talk through some of them. I cite a lot of different examples that this can be used with, but then there was only one example, and I was like, well, that's silly. Why not just do a couple more examples? So I Googled net change theorem examples, and I found a couple more. And I was like, let's do examples rather than just talk about them. Okay, but honestly, the net change theorem is just a definite integral. You're just applying a definite integral to application or to different circumstances. They just because it's up here. If V of t is the volume of water in a reservoir at a time t, then its derivative V prime of t is the rate of change, rate at which the water flows into the reservoir at time t. So therefore, if you have the derivative, if you have the integral of the rate of change, that's the net change. The integral of the rate at which the water flows is the net change. So that would tell you the integral would be equivalent to the amount of water, the change in amount of water in the reservoir between those two time periods. And that information can be useful. What's the second one here? Concentration of a product in a chemical reaction, net change. I found an example like this. The mass of a rod measured left to right is the linear density. So the mass of the segment of the rod lies between x is equal to a and b. Rate of growth of population, net change. There's application in economics as well. If C of x is the cost of producing x units of a commodity, then the marginal cost is the derivative, C prime of x. So if you can find the net change of C prime of x, if you can find the net change of the marginal cost, that is going to be equivalent to the increase in cost when production is increased from x1 to x2 units. Okay, so a lot of different application that we can use. One of the big applications that we're going to talk about is velocity and acceleration. Right? We've been velocity and speed and acceleration and position. That's what we've been talking about, the application we've been talking about all year. Right? If an object moves along a straight line with position function s of t, then its velocity is v of t, which is s prime of t. So therefore, if you can take the integral of v of t in two different time periods, you take the integral of v of t, because that's the integral of the rate of change, right? And that's what net change is. Again, it's the integral of the rate of change. So if you take the integral of v of t, that's going to give you change in position over time, which is total net change in distance. Total net change in distance. The net change of position or displacement of the particle during the time period from t1 to t2. Yeah, and then the second bullet point is something that we'll talk about as well. If we want to calculate, oh please. Hudak. Hi, Mr. Hudak. That's okay. That's fine. Gotcha. Yeah, no problem. Fine. They want you to go move your car. That whole conversation was tell them to go move their car. If we want to calculate the distance the object travels during the time interval, we have to consider the intervals when v of t is greater than or equal to 0, and then v of t is not less than or equal to 0. Because if you think about displacement, if you talk about net change, I'm moving along a straight line path, but I could be moving forward or backward, right? My velocity could be going in a positive direction, or my velocity could be going in a negative direction. So the integral over the whole time period would be the net change in displacement. It would be like, okay, if I moved this speed positive and this speed negative, obviously if I move more positive than negative, I'm going to end up in the positive displacement. However, if I move with a negative velocity more than a positive velocity, I'm going to end up with a negative displacement. So, but the end result is just going to show me net displacement, net change. So if we want to calculate total distance traveled rather than just straight up displacement, if we want to calculate total distance traveled, want to calculate the distance the object travels during the time interval, we have to consider the intervals when v of t is greater than or equal to 0, and then also when v of t is less than or equal to 0, when the particle moves right versus when the particle moves left. In both cases, the distance is computed by integrating speed just along those time periods, and that's what we'll do in our first example here. All right. Let's take a look at a couple of these. This is the only example that I have prepared. The other ones I just copied off the internet, and we'll just see what happens. A particle moves along a line so that its velocity at time t is v of t is equal to t squared minus t minus 6, measured in meters per second. Find the displacement of the particle during time period 1 to 4, and then find the total distance traveled during that time period. Okay, again, I am integrating the rate of change, right? I am integrating the velocity. So therefore, that's going to tell me total displacement, right? So part A is telling me to take from 1 to 4 of t squared minus t minus 6 dt. That's going to end up giving me total displacement. So let's run it. We can do that. That's pretty easy. T to the third over 3 minus t squared over 2 minus 6t from 1 to 4. All right, so we've got 4 to the third over 3 minus 4 squared over 2 minus 6 times 4 minus, now, and this is important, I'm just about finished grading your quizzes, but one of the biggest mistakes I keep seeing is not putting the second part in parentheses. Like a lot of people are just putting a minus sign and then plugging everything in on the right side. Don't do that. I don't know what to say about that other than don't do that. Put it in parentheses. So we have a 4 to the third, so 64 divided by 3 minus 4 squared, which is 16, divided by 2 is 8, minus 6 times 4 is 24. So on the right side, I believe it should be, it should be negative 10.6, I believe. Minus, okay, and then we got 1/3. Just gonna make sure 64 over 3 minus 8, 16 over 2. Okay, good. Minus, and then we got 1/3. That's a minus 0.5 minus 6. All right, so we got 6.5. That's a 13. 1/3. I was gonna say that looks weird. Minus 0.5 minus 6. There we go. Negative 6.16. And then we can have negative 10.67 And minus negative is plus. Plus 6.16. And that will give me negative 4.5. So what does that tell me about where the particle ends up? To the left, 4.5 meters. To the left, 4.5 meters. Do I know that it only traveled to the left? No, I don't. I just know that at the end of 4 seconds, its displacement is negative 4.5 meters. That's all I know. That's all I can tell from this. However, if I wanted to find the total distance traveled, I could do so. I can find that out. I just need to figure out when velocity is positive and when velocity is negative, right? So how do I figure out when velocity is positive and when velocity is negative? We'll take a look at the function, right? T squared minus t minus 6 is equal to 0. Find out the zeros. Feel that? Okay. There you go. So when I factor that, obviously factors a negative 6 that adds to get to negative 1, or negative 3 and positive 2. So t minus 3, t plus 2. So t equals 3, t equals negative 2. Okay, but do I need to use both of those zeros? No, because I'm only concerned about when the particle is traveling from second 1 to second 4. Does it change direction in that time period? Yes, it does. It does change directions in that time period. Okay. So what I'm going to do is I'm going to figure out the integral from 1 to 3. And then I'm going to figure out from 3 to 4. Now, I have to think about this strategically, right? In which direction am I moving from 1 to 3? In which direction am I moving? Am I moving in the negative direction? Am I moving in the positive direction? What's an easy way to figure that out? Just plug in 2. Right? Just plug in a number inside that interval. Oh, okay. So at second 2, which am I moving in the negative or positive? Negative direction. Now, so that means this is going to give me a total negative area, right? This is going to give me a total negative distance. So in the end, I'm going to take the opposite of that because I want total distance traveled, right? I don't want to add that with a positive. I don't want to add a negative number with a positive number because that's going to give me negative 4.5 again. So I want to take the opposite of that because I want total distance traveled. All right. Or you could just think about it as the absolute value of that. That's really what the other slide had said. All right. So we take, and it's t squared minus t minus 6. T squared minus t minus 6 dt. T squared minus t minus 6 dt. Which we already know the antiderivative for. We already did that. So it's negative t to the third over 3 minus t squared over 2 minus 6t. This one's from 1 to 3. Plus t cubed over 3 minus t squared over 2 minus 6t from 3 to 4. Let's run those values. That was quick. Yeah. We're speaking. All right, so let's plug in 3. So 3 to the third divided by 3. Oh, that's just 3 squared, isn't it? Because 27 over 3 is 9. So 9 minus 9 over 2, so 4.5, minus 18. Plug in 1. So we're going to say minus, and I'm going to put this in parentheses, 1/3 minus 1/2 can I not type in 1/3 today? 1/3 minus 1/2 minus 6. So this is total negative area, right? Negative distance. So take the opposite of that, 7.3. Negative 7.3. So just positive 7.3. That's total distance traveled moved in the negative direction. And then we do from 4 to 3. All right, so we have 4 to the third divided by 3 minus, and then that's that 16 over 2 again, so 8 minus 24. And then we subtract that with the entire 3 plugged in. So 3 cubed, which is 27, divided by 3 is 9, minus 4.5, 9 squared over 2, minus 18. 2.83. Okay, so we got 7.3 and 2.83, which gets me 10.13. We'll just say 10.1. 10.1 meters total distance traveled, right? Not distance traveled, but total distance traveled. I moved 7.3 meters in the negative direction and then 2.83 meters in the positive direction, giving me a net distance traveled of, what was that, negative 4.5, but total distance traveled of 10.1 meters. Make sense? Cool. All right, so let's do something I've never done before. Let's see this. We're doing this both fresh. If the motor on a motorboat is started at time 0, and the boat consumes gasoline at a rate of 5 minus 0.1 t to the third gallons per hour, how much gas is used in the first 2 hours? If the motor on a motorboat is started at time 0 and the boat consumes gasoline at the rate of 5 minus 0.1 t to the third gallons per hour, how much gasoline is used in the first 2 hours? It's fun, exciting. I've never done this problem before. It's brand new. It's like Christmas morning. No? Just like it. A whole new problem. All right, so I know I want to find the integral because that's going to give me net change. What is this net change of? Net change, the rate of change is consumption of gas, right? Consumption of gas per hour. So if I find the integral of the rate of change, that's going to give me total difference, total net change in gasoline, basically. Okay. So let's find the integral. What am I going to find? What's the boundaries? What's the finite boundaries? From 0 to 2. From 0 to 2. From 0 to 2 of 5 minus 0.1 t to the third dt. Let's find the integral. So 5t minus 0.1 t to the fourth over 4 from 0 to 2. Again, the nice thing here about plugging in, having it come at 0, when I plug in 0, it's going to give me 0. So let's just plug in 2 and see what happens. 5 times 2 is 10. Minus, and then we got 0.1 times 2 divided by, to the fourth, divided by, you know what? I probably should put this in parentheses. Let me put that whole 0.1 and stuff in parentheses. Insert parenthesis. 0.1, 2 to the fourth, divided by 4. Yeah, there we go. Looks good. 9.6. 9.6 gallons, right? That was an easy one. That wasn't too bad, right? Let's try another one, shall we? Do you want to do a fish population? Or do you want to do the linear density of a 1 meter rod? Fish. Fish it is. Suppose the fish population in a lake is increasing with a rate of f of t is equal to 10 plus 5t to the 3/2 power. thousands of fish per year. Where t is the number of years from now, how much will the fish population increase in 4 years? So again, the important thing here is to remember that the function that we are given is a rate of change function, right? It is a rate of change function. The fish population is increasing at this rate. That's the rate of change. So to take the integral of the rate of change will give me total net change. All right, so what's my boundaries? What's A and B? What's A and B? 0 and 4. I don't know. I don't hold it against you. 0 to 4 of this function 10 plus 5t to the 3/2 power dt. It's going to give me total net change of fish over the 4 years. All right, let's find the integral. 10t plus 5t to the, okay, so it's already at 3/2. So it's going to go up to 5/2, right? 3/2 plus 2/2 is 5/2. Divided by 5/2 from 0 to 4. Can that reduce? 5 times 2/5. Oh, that's just going to be 2, right? That's nice. So 10t plus 2t to the 5/2 power from 0 to 10. Again, nice thing about starting at 0, that when I plug in 0 to that function, it's going to just be 0. So 10 times 10. What's wrong? We good? What am I doing with 10? So let's plug in 4 instead. That would be over the course of 10 years. We could do that. Plus 2 times 4 to the 5/2 power. 5/2 is 2.5, right? $104,000 fish. It's a lot of fish. All right, that's good. Let's stop there. We don't have to do the length of a rod, probably. Fishies. Bro, I want to fish. Drew, we're allowed to have fish.